This is the R/2R ladder, which essentially converts digital inputs from these slide switches uh, into analog outputs. In this case, there are 8 bits, meaning that the output could define one of 256 analog voltage levels that would be represented through this red LED. It is called a R/2R ladder because there are really only two types of resistors in the network. It doesn't matter what the R value is as long as 2R is twice as much as the R value. In this case, a 5.1K ohm resistor was used. The R, which are these, and then along with the 10.2K resistors, the 2Rs, which are these. All the resistors have a 1% tolerance, which allows for pretty accurate results. The output resistance, regardless of how many bits we use, will always be R. This is due to the idea of Thevenin's equivalent circuits theorem, which indicates that it is possible to simplify any linear circuit, no matter its complexity, to an equivalent circuit with a single voltage source and series resistance. I'll talk about how the circuit works using the 4-bit R/2R ladder as the example. Here, we have all the voltage sources at 0, which makes them seem as if they were in ground. So both of these two R resistors are connected to ground, which can be simplified to R, as two parallel resistors of 2R equals to one resistor of R. Now, we can see that there is an R here and an R here, which can be replaced to 2R because they are in series. Now, these two R's are in parallel, which can be simplified into another R. We can see a pattern here. No matter how many bits we have, it can always be simplified. Now, these two add to 2R, and then these two R's are simplified into R. And this process repeats until finally the output impedance is simply just equal to R. We can also find the voltage levels of each bit using the idea of superposition. In order to do this, we should have one slide switch on and turn the others off. And we have to do this for each of the varying voltage sources. For us, 4 times. And then sum all those results, which is how superposition works. We will also use Thevenin's equivalent circuits to calculate things. So if we cut the circuit here, we have the voltage here, and it goes to ground across two 2R resistors. Thus, the voltage in the middle of the resistors would be half of the voltage of the switch. So the voltage of that would be V B0 divided by 2. We already know that those two R's reduced to be R, so now it's reduced into R and V B0 divided by 2. Now, once again, the R's are in series, which add up to form 2R. Thus, the voltage that is going to form at the point in between the two R's is half of the voltage of B0 divided by 2, so V B0 divided by 4. Once again, these resistors in series add up to 2R, and the voltage in between the two R's is B0 divided by 8. We can see a pattern, so then the voltage that would appear here would be VB0 divided by 16, or the series resistor of R. We can't go any further as there are no more switches, thus we can conclude that the contribution from the first bit is just 1/16 of the reference voltage. Using this technique, we can calculate for the other bits. In general terms, for the 4-bit one, the V output is equal to, if the first switch is on, it will be 5 divided by 16. And when the next switch is on, the voltage level would be 5V divided by 8, and 5V divided by 4, 5V divided by 2. The more switches, the farther it goes. With 8 bits, the lowest voltage produced by a singular switch is 5 volts divided by 256, and the maximum voltage of this circuit is 5 volts, give or take. And if all the switches were turned on, in theory, the LED should receive all 5 volts. Here's a graph that shows the voltage contribution of each switch in the 8-bit R/2R ladder in theory. And as we turn on each switch, the LED progressively gets brighter because of the increase in voltage as more switches are being turned on. We can see that the LED did not really turn on during the first few switches, and this is because a red LED needs about 1.8 volts to turn on. However, when looking at the graph, in theory, only the last two switches are even close to 1.8. Thus, you can only really see the effect on the last two switches. The values from the table will be similar to the values of the voltage in the actual circuit. For example, we can try to find the voltage of the LSB, which according to the graph is 0.02 volts, or 20 millivolts. So if we were to do this, we would have one to the output, or like one wire in the output and one to ground, and we were getting, where it's around 219 0.02, 0.019, around there. 19, around 0.016, around there. We can also try this maybe with another one. Maybe we can try the fifth switch, or bit 4, and it says, according to the graph, it should be around 313 millivolts. And let's see if it is similar to that. And we can see that we're getting around that number, 300 and 341, 227, so around there. So it is pretty accurate. There are obviously going to be some fluctuations because our resistors are at 1% tolerance, and there are resistors with even lower tolerance, so it can get more accurate. But for our purposes, this is around the same as the mathematical calculations. The op-amp can also be used in this circuit. The two main rules of an op-amp is that number one, no current can flow in or out of the inputs, and number two, the op-amp tries to keep the inputs the same voltage, so it has no way to drive a voltage in or out to keep it the same. So it does this through feedback, which is this component right here. Thus, the op-amp in the circuit acts as a voltage follower, where the output voltage is the same as the input voltage. And as you can see, all the switches are off, or on the left side here, and the LED is actually still on, which was not the case with our 8-bit without the op-amp. So in theory, when the circuit outputs 0 volts, the op-amp should also output 0 volts, but because the LM741 op-amp chip has some restrictions, this is not the case. The chip features a voltage swing that is constrained to be 1 volt less than the high and low voltage rails at its two ends. This limitation exists due to the presence of a buffer within the op-amp circuitry. In practical terms, the LM741 op-amp's limitations become evident when the high voltage rail is at 5 volts and the low voltage rail is at 0 volts. In such a scenario, theoretically, the op-amp can produce output voltages ranging from 1.5 volts to 4.5 volts, and consequently, when the DAC outputs 0 volts, you can expect the op-amp to yield a 0 volt output. However, due to the constraints, it typically generates an output close to 1.5 volts. This is the R/2R ladder, but more compact. This here is the resistor configuration of the original circuit, and all the resistors do the same thing, but just compressed into chip. And this is a network of resistors grounding the leads to make sure the voltage isn't floating, which is when a signal isn't connected in any way to the building ground system, but rather has an isolated ground reference point. These are the switches, and they're just more compact to make it look neater, and it basically does the same thing as our 8-bit. Thanks for watching.